Good morning everyone. This is Dr. S. Muthlakshmi. Today I am going to give a lecture on equivalent circuit of an induction motor. So far we have discussed the basic construction of induction motor and how the induction motor is working and how the rotating magnetic field is created in an induction machine. And basic terms related to induction machine, that is slip, synchronous speed and rotating magnetic field. So next we can see the topic equivalent circuit of an induction motor. I had to ask one question, why we can go for a equivalent circuit of a induction machine, not only induction machine, why we have to analyze, why we have to go for a equivalent circuit for any kind of machine. This is a very basic question. What is it? So that is nothing but in order to analyze the performance characteristics of a machine, we can go for a equivalent circuit of an induction machine. So before that, we should know the basic term, that is the rotor frequency in an induction machine. So it is based on the slip of an induction motor. So that is already we have discussed in a previous lecture. So what do you mean by slip? Slip is nothing but that is the difference between a synchronous speed and rotor speed, which is always expressed as a percentage of a synchronous speed. So here, due to the slip of an induction motor, the induction motor which is always running at subsynchronous speed of a machine. That is why it is running at subsynchronous speed. If it is running at synchronous speed, the slip will be 0. So there is no induced EMF in a rotor, so we can't run the machine. So that's why we can say that induction motor is basically depends on the slip. Isn't it? So let us see what is the relation between the slip and rotor frequency and number of pole pair and synchronous speed. First we can write the stator frequency F is equal to Ns into P, whereas Ns represents the synchronous speed of a stator rotating magnetic field. And next we can see Fr is nothing but rotor frequency, that is Fr is equal to Ns minus Nr into P. Here Ns minus Nr is nothing but that is a slip speed. That is the rotor speed of a induction motor. Here we are having first expression is a stator frequency and second expression is the rotor frequency. Now we can relate these two expressions. Finally we get Fr is equal to S into F. So here S is nothing but slip and F represents the stator frequency. So here from this we have to conclude the rotor frequency which is equal to slip times the supply frequency. Isn't it? It is a very basic question. Sometimes they will ask in university, what is the rotor frequency in an induction machine? If they ask like that, you can write the answer Fr is equal to S into F and also mention the factor S and F. Let us move on to equivalent circuit of an induction motor. So we know the basic concept. Before we are going to see the equivalent circuit, I am asking one question. Induction motor is said to be a induction motor. Why it is said to be a rotating transformer? Or otherwise we can say why the induction motor is called as rotating transformer, because there is some relation between the transformer as well as induction motor, because that induction motor operation which is similar to that of the transformer operation. But you know that transformer is a static machine whereas induction motor is a rotating machine, but the operation it will be the same for both transformer as well as induction motor. So that is why we can say the induction motor is said to be a rotating transformer, because the operation will be the same but it has a rotating part. So that's why we can say that rotating transformer. Sometimes they will ask in interview questions, why the induction motor is said to be a rotating transformer. Okay, as engineers we are ready to say the answer why the induction motor is said to be a rotating transformer, isn't it? So there is nothing but the induction motor which is similar to that of a transformer because it has a rotating part. So that's why we can call the induction motor is said to be a rotating transformer. So let us see that. So this is the equivalent circuit of an induction motor, and here the stator carries the field coil whereas rotor carries the armature coil. Just like here the stator coil, just like in a transformer primary winding, and whereas rotor coil just like in a secondary coil in a transformer. Okay, so just we have to correlate equivalent circuit of induction motor with the equivalent circuit of a transformer. So here the stator carries the field coil whereas the rotor carries the armature coil, and here the stator winding which is connected to the supply V1 whereas the rotor which is connected to the load. So now we are giving three-phase supply to the stator coil. You know that rotating magnetic field is created. So due to the rotating magnetic field which sweep over the rotor conductor, it cut by the rotor by electromagnetic induction. That is the Faraday's law of electromagnetic induction. So there is an EMF induced in the rotor coil. So here we are having the short circuited rotor in a squirrel cage motor. So the induced EMF which causes a current flow through the rotor winding. So according to magnetic property, the current carried by the rotor coil which will cause the another one flux, that is to be a rotor flux. So here we are having two set of fluxes. One is rotating magnetic flux on the stator and another one is rotor flux. Okay, so we are having two set of fluxes. Now the interaction between these two fluxes which causes some force on the rotor. So you know that if force acting on the rotor, what happened in that circuit? The rotor, it will be twisted from its rest position. So which will cause the rotation of rotor. Here the rotor which will try to rotate at synchronous speed, but it never rotates at a synchronous speed. It will be always running at subsynchronous speed. So that's why we can say that stator speed is ns whereas rotor speed is ns minus nr. Okay, just keep in your mind. So after the induced EMF in the rotor coil which is affected by slip value. So because what are all the factor depends on the frequency. So all the factors which is affected by the slip value. So because already we have discussed rotor frequency which is equal to S into F. Okay, so what are all the factors related to the frequency which is affected by slip value? Because rotor frequency which is equal to slip times the supply frequency. So that's why we can say that all the rotor parameters which is affected by slip value because it depends on the frequency. Let us see how the rotor voltage, how the rotor current and rotor reactance which is affected by slip value. So let us see first the stator circuit model of an induction motor. This is the stator part. Just like in a transformer we can say that is a primary winding of a transformer. Okay, so this is a primary part, that is a stator of a induction motor, and here the stator winding which is connected to the supply V1. When you are giving the supply, there is a current flow I1 through the winding, so which will cause us self-induced EMF in the coil, that is represented E1. And here we have a no load branch circuit, that is it comprises R0 and X0. R0 is nothing but non-inductive resistor, whereas X0 is nothing but non-inductive reactance. That means these two are a pure resistive and inductive reactance. And here the current flow through the no load branch which is represented as I0. And here the R1 is nothing but stator winding resistance and X1 is nothing but stator winding reactance. And from the circuit, we can write the no load current I naught is equal to I mu plus IW. So as we know that in a transformer, the no load current can be calculated around 2 to 5% of a rated current. Whereas in induction motor, the no load current can be calculated around 20 to 45% of the rated current, which is depends upon the size of the motor. So next we can see rotor circuit model. When three-phase supply is given, what happened in the circuit? Because of rotating magnetic field, there is an EMF induced in the rotor, which will cause some current flow through the rotor coil, which will create some force on this rotor. Okay, so the rotor starts to rotate. So the relative speed, relative motion of rotor and stator, if it is greater, the EMF induced in the rotor is also greater. Okay, so if the relative motion between this stator and rotor, if it is higher at standstill condition. So this condition is known as locked rotor or blocked rotor condition. So at this condition, slip value, at blocked rotor condition, the slip value which is around maximum value, that is which is around equal to 1. And here the induced EMF can be written as E2 represents secondary voltage, that is the rotor voltage which is affected by slip. So that can be written as is equal to S into E2 naught. E2 naught is nothing but that is a primary voltage, that is a stator voltage. And here the rotor resistance, it's a constant value, it is not affected by slip value. And next we can see the reactance, rotor reactance. So rotor reactance, which is depends on frequency. We know the basic formula X is equal to 2 pi f L, and here rotor side we have to write X2 is equal to 2 pi f2 L2. And here the rotor reactance, which depends on the rotor frequency F2. So when you are changing the frequency, the reactance is also changed. So it is depends on the it is depend on the frequency. So which is also affected by slip value. So because F2 is equal to F1, S into F1, that is rotor frequency. So now you can substitute F2 in terms of S into F1. The expression it will become X2 is equal to 2 pi S F1 into L2. Now keep the slip value in outside S into 2 pi F1 L2, and 2 pi F1 L2 can be written as reactance of a primary, that is X1. So finally we can get X2 equal to S into X2 naught. Here the X2 naught is nothing but reactance of the motor at standstill condition. Next we can focus rotor circuit model. So far we have discussed stator circuit model. Next we can focus on the rotor circuit model. So already we know that every winding it has its own resistance and reactance. In a stator winding it has resistance and reactance that can be represented R1 and X1. Like that, here the rotor winding resistance can be represented R2 and X2. Here the rotor parameter except resistance, other rotor circuit parameter which is affected by slip value, because E2 is equal to S into E2 naught, and here the reactance X2 is equal to S into X2 naught, and frequency already we have discussed. F2 is equal to rotor frequency is equal to slip times the supply frequency. F2 is equal to S into F1. So all the except resistance, all the parameters depends on the slip value. So wherever there is change in slip, these parameter on the rotor can also change. So from this circuit we can write the rotor impedance Z2. Z is equal to, we know that Z is equal to R plus JX. Okay, that is already we have discussed in a three-phase AC circuits, how to write the basic expression for impedance. Is that equal to R plus JX? So here we can write the impedance on the rotor side. So Z2 is equal to R2 plus JX2S, and here the X2S it is affected by slip value. So it can be replaced by S into X2 naught. So now we are having the impedance. we know the current flow through the rotor coil I2. So now we can calculate I2 is equal to, according to Ohm's law, voltage per impedance. Here the voltage on the rotor E2S and divided by impedance is Z2S. So Z2S already we got the expression 4. Now substitute in I2S. So the expression become I2S equal to S E2 naught divided by R2 plus JX X2 naught. This is the current expression. Already I have told the rotor current which is affected by slip value. See the expression I2S which is depends on S into E2 naught, which is depends on the slip value. So that's why I can say, that's why I have to say the rotor current which is also affected by slip value. Now dividing the expression phi by S value, slip value, now the expression will become I2S equal to E2 naught divided by R2 by S plus JX2 naught. So from this circuit we can say that here the reactance is a fixed value, but resistance can be varied with the slip value. So this can also be represented in a diagram. And this is the approximate equivalent circuit of an induction machine. Now we are going to transfer the parameter from stator to rotor or rotor to stator. Already you know that when you are going to transfer the parameter from one side to another side, it becomes dash. For example, if you want to transfer the parameter R1 from stator to rotor, it will become R1 dash, isn't it? So like that, X1 transfer from stator to rotor, it will become X1 dash. So like that, rotor to, if you want to transfer the parameter R2 from rotor to stator, it will become a R2 dash. Okay, so you just keep in your mind. So when you are going to transfer the parameter from primary to secondary or stator to rotor or rotor to stator, it will become dash by the transformation ratio, just like a transformer. And here I am showing the approximate equivalent circuit of an induction machine refer to the primary, that is a data transfer from secondary rotor to stator. Equivalent circuit, approximate equivalent circuit of a stator I am showing here because all the secondary parameters transfer from second rotor to primary. So it comes X2 dash, R2 dash, I2 dash and E2 dash. All the remaining parameters are stator parameters. This X2 dash, R2 dash, E2 dash are all the rotor parameter. When it transfer from rotor to stator, it comes dash. So from this circuit, A dash, beyond A dash, we can write the impedance Z is equal to. So we can combine a resistance and reactance, and finally we can calculate the impedance Z equal to R plus JX, R1 plus R2 dash by S plus J into X1 plus X2 dash. So if we know the total impedance of approximate equivalent circuit, we can calculate the current I2 dash equal to V1 divided by ZA dash. So now substitute the ZA dash in a I2 dash expression. We will get a final expression I2 dash equal to V1 divided by R1 plus R2 dash by S plus JX1 plus X2 dash. So now we can calculate the magnitude of current I2 dash is equal to V1 divided by square root of R1 plus R2 dash by S whole square plus JX1 plus X2 dash whole square. So from this impedance triangle, we can write I2 dash equal to I2 dash cos pi 2 minus J2 dash sin pi 2. This is the basic expression. Whereas from the impedance triangle, we can write tan pi equal to X by R and cos pi equal to R by Z. So this is the basic formula for a impedance triangle. Okay. So tan pi means X by R of a circuit, cos pi means R by Z by a Z by R by Z of a circuit. So for an approximate equivalent circuit, X is nothing but X1 plus X2 dash, R is nothing but total resistance R1 plus R2 dash by S. So tan pi 2 can be written as X1 plus X2 dash by R1 plus R2 dash by S. Like that, cos pi 2 equal to R by Z. So the total resistance R1 plus R2 dash by S divided by total impedance ZA dash. So now the load or no load current, that is already we have written I naught equal to I mu plus IW, and I naught is equal to I mu. Instead of I mu, we can write V by R. So the voltage across magnetizing component and non-inductive resistance will be same, V1. and divided by R naught, we will get the value I mu, and V1 divided by X naught, we get the value I W, that is working component. Now take the common term V1. The expression becomes I naught is equal to V1 into 1 by R naught minus J by X naught. So the stator current, so from the approximate equivalent circuit we can write the stator current. After transformation we can write I1 equal to I2 dash plus I naught. Here from this equivalent circuit we can write I1 equal to I naught plus I2 dash. At this point A, the current I1 can be splitted I naught and I2 dash. So from this equivalent circuit we can write I1 is equal to vector addition of I naught plus I2 dash. So that's here we can write I1 equal to I2 dash plus I naught. So from this circuit we can calculate the total losses by using the basic formula. Here the I naught no load component, no load losses can be calculated 3V1 I naught cos pi naught. It's a basic formula, power equation, and stator input 3V1 I1 cos pi 1. Now we can add these two, we will get a stator power loss, and here substitute stator input is equal to 3V1. Instead of V1 substitute the value I1 into R, and finally the expression become a 3I2 dash squared into R1 plus R2 dash by S plus no load loss. PHE is nothing but that is a no load loss. So now we can calculate the air gap power. So it's a very important factor. I didn't say air gap in an induction machine. Here the rotor and stator which is separated by air gap, small air gap. So we can also calculate the air gap power. So we can calculate the air gap power. PG is equal to V1 into I2 dash cos pi 2. The air gap, the current flow through the air gap is I2 dash. So we can calculate the power V1 I2 dash cos pi 2. So now substitute I2 dash value, we can get the expression. It will be like that. So we know the basic torque equation, T equal to P by omega. T equal to P by omega. So the TD developed torque equal to PG by omega S. PG is nothing but air gap power. So we have the expression, and divided by omega S, we get the expression 16. So from the approximate equivalent circuit, we can calculate losses and power. If you know the losses and power, we can easily calculate the efficiency of our induction machines. Thank you.